Alright, so this is going to be a video on the derivative of exponential functions. Now you might be thinking, what is an exponential function? Didn't we already cover exponential functions when we covered functions like x squared and x to the third? Well, no, those are actually power functions, and exponential functions are a little bit different. So here is basically what an exponential function looks like. We have y equals a to the x. Now with an exponential function, you'll notice that this a right here represents a constant, so a equals a constant. And the x is the exponent. Now this is different than a power function such as y equals x squared. Now if you notice the difference between these, they're very similar, but x in this case is the base and x over here is the exponent. 2 is a constant for the power function, and then over here this a is the constant. So exponential functions are different than power functions. You do not want to get those two confused because these same rules don't work for each of them. Alright, that being said, let's figure out how to find the derivative of an exponential function. The first thing that we're going to do with our exponential function here is take the derivative of both sides with respect to x. So we have d over dx on this side, and then d over dx on this side. If you remember, the d over dx just means take the derivative of whatever's over here with respect to x. So that's what it's basically saying here. So right here we have the derivative of y. This is the derivative that we're looking for. dy over dx is right here. And then we're trying to figure out the derivative of this a to the x. Now, just like before, to be able to prove and figure out what this derivative is, we're going to need the limit definition of a derivative. Only this time we're going to be using a to the x as our f of x function. So it's going to look something like this. Okay, from here we're going to do a little bit of simplifying. So we have a to the x plus h. Well, that's just... Now, if you remember your exponent properties, whenever you're adding exponents like that, you can just take the bases, separate them. So you have a, base a here, and base a here, and then you're just multiplying a to the x times a to the h. From here, I'm going to factor out an a to the x. So you get something like this. So I factored out the a to the x. I have something that ends up looking like this here. Now this a to the x right here, it's actually not affected by this limit as h goes to 0. So what I'm going to do with this a to the x is I'm going to put it in front of this limit just to make my life a little bit easier. Okay, so you end up with something like this, with the a to the x put in the front. Now the reason why we did that is because this is a special limit right here. This limit actually defines a certain function that you've probably already used in either pre-calculus or maybe algebra 2. This right here is actually equal to the ln, the natural log of a. Okay, so this a constant right here, the natural log of a is based on this limit right here. So what we can do, essentially, is instead of having this big limit right here, we can just substitute this ln a in for all this, and you end up with a to the x ln a. Okay, this ends up being the derivative of a to the x. So right here is what your formula that you're going to need to figure out the derivative of an exponential function. You just take whatever the exponential function is, rewrite it, so a to the x, and then you just do ln whatever that base is. So if this base was 2, it'd be 2 to the x ln 2. Okay, we're going to go over more examples in the next video. I just want to show you basically the conceptual understanding of how to find this derivative right here. As for this ln a, this might be a little confusing for you, so I'm going to kind of prove this with a graph. So basically I'm using the Desmos calculator to prove that the limit of a to the h minus 1 over h, as h gets infinitesimally closer to 0, is equivalent to that function ln of a. And that's basically how ln, the natural log function, is defined. So here I have this red function right here where it says y equals a to the h minus 1 over h. Now if you notice, h is set equal to 0, so a to the h, which is a to the 0, is going to be 1, minus 1 is 0, and then h is 0, so it's going to be 0 over 0, which is an indeterminate. That's why nothing's actually graphed here. Okay, if you also notice, my a is equal to 3 here, but again, it doesn't matter because it's a to the h, 3 to the 0, because my h is equal to 0 right now, so it's still equal to just 1. So what I need to do is, based on limits, the value is actually not equal to 0. The value of h is not equal to 0. It's getting infinitesimally closer to 0, so that means I need to make this h right here, instead of making it 0, I need to make it get infinitesimally closer to 0. So I'm going to put a 0.1 in there, and then you have a graph that shows up like this. Now we need to get infinitesimally closer to 0. So 0.1 is not going to cut it. We need to get even smaller than that. So I'm just going to put a bunch of zeros before this 1 right here and in between the decimal place right here. And if you notice, this function is going to shift a very tiny amount as I'm adding the zeros. And I'm basically going to be doing this until the function stops moving. So basically stop moving already. So it's pretty good. It's a pretty good approximation so far with the amount of zeros that I put in there. I'll put a couple more just for fun. Okay, then I have right here g of x is equal to ln a. Again, a is equal to 3 here. So g of x is ln 3, and then up here, this a right here is also equal to 3, so it graphs this out. I can change this a value, and it is going to move accordingly the graph. Now the main thing that I want you to see on this is we're trying to prove that the limit of this function as h gets closer to 0 is equal to ln of whatever that base a is. So I'm going to turn on this g of x right here. It's going to be a purple function, and if you notice, it's going to line up directly on top of that red. So if I turn off the red and turn it back on, you can notice that it lines up directly on top of it. Okay, if I change the value of a, also they move together each time. So as I change the value of a right here, it doesn't matter. The function still stays the same. They still stay equal. So this proves basically that the natural log of a is equal to this limit of a to the h minus 1 over h as h gets closer to 0. So now that we found the derivative of exponential functions a to the x, we can use this to find a special derivative of e to the x. If you remember, e is basically, it's the natural base. It's equal to Euler's number. It's basically a constant. You probably learned about this in previous math classes as well. But an interesting thing happens when we take the derivative of e to the x. So I'm going to do that right now. So first thing that we're going to do is notice that this is an exponential function. We have a constant here, and then it's raised to the x power. That means that we can use this formula right here to figure out the derivative of this. We just need to substitute in our values for a, because in this case, our a is equal to e. So that means our derivative with respect to x is going to be equal to, see, it's a to the x. Well, now our a is e, so you would just rewrite this basically right here as e to the x, and then you would multiply it by ln, whatever the base is. Well, the base is e. So we're going to be multiplying it by ln e. Now, an interesting thing happens here is that this ln e, if you remember from Algebra 2 or from pre-calc, ln of e is equal to 1. So if you took your calculator and plugged in ln e, you would actually get 1 for this value. So an interesting thing about the derivative of e to the x, it's actually equal to e to the x. So the derivative of e to the x is itself e to the x. So that's the derivative of exponential functions. If you have any questions about anything in this video, let me know.